In this video, we're going to discuss bond enthalpies and how you calculate them. So if we look here, here is an exothermic reaction and a bond enthalpy diagram. So just remind you about GCSE, the energy taken in, okay, positive, because you're taking in the energy, break the bonds, and then when you make the bonds, the energy goes down. It goes down by this amount, okay, and this amount. Now you've got to get a negative energy change, or enthalpy change, for exothermic reactions, which means it makes sense that the smaller number will minus the bigger number. Okay, that's how I remember the way around for the equation. So if you look at the equation here, bonds broken, this one, okay, minus bonds made, which is that one. Right, put the numbers in, and you'll get your overall enthalpy change for the reaction, which will be negative. So when we're doing these calculations, we don't apply a negative or a positive to the numbers here, we just give a number. Now, in this video, we're going to talk about bond enthalpies. Now, bond enthalpies can also be called bond energies, depending on where you go, but in your A-levels, it tends to be called enthalpies, which is the energy required to break a particular covalent bond in 1 mole of molecules in a gaseous state. Okay, so 1 mole of molecules. So that means, for example, in this one, if there was OHs, there would be 2 moles of molecules here. Because there's 1 mole of water, there will be 2 bonds for each mole of water. Therefore, there will be 2 moles of bonds that will be broken here. Now, if that's the case, breaking it, we'd have to break them to get H's and O's, and then we'll remake them here. Now, I'm going to put values on here just to show you whether it's an exothermic or endothermic process, but normally you wouldn't put pluses and you wouldn't put minuses. You just leave it as a positive number. If that's the case, this is 363 kilojoules per mole. And this is minus 463. That means the energy is being taken in to break the bonds here, and it's being given out when the bonds are made here. Now the overall energy change is going to be 2 times 463 for this process. Okay, notice I've dropped the mole because it's not per mole, per 2. That's 2 moles of bonds, right? Okay, here we can say 926 kilojoules was given out to the surroundings if we broke all of those bonds. The only reason I'm showing you this is to show you about exothermic and endothermic change. So if I put the energy in, that means the energy is going up, which means it's an endothermic change or endothermic process. And you need to identify those mainly in the second year of your A-levels. And the other one is giving out energy, so it's an exothermic process. And you'll have to label that. So just remember, when you're breaking the bonds, always endothermic process. Bond length and strength. The lower the atomic radius, the closer the atoms are to each other, and that gives you a stronger bond. So how does the bond length affect its strength? Okay, well, you get a higher bond enthalpy, a higher amount of energy it takes to break the bond if those atoms are closer to each other. And you can see the atoms are really far away. Okay, and I'm looking at the center of the atom and seeing how far they are away. You can see this is really close, slightly further, and slightly further. Well, if you remember the definition of covalent bonding is the electrostatic attraction between a shared pair of electrons and positive nuclei. So that means the positive nuclei of each of these atoms is holding the electrons in place. And that means those nuclei here are far, far away from where those electrons are, and they're really close to where those electrons are now. So that means this is more likely to have a very strong bond. Those electrons are going to be held in place, and therefore have the higher bond enthalpy. So this has a high bond enthalpy, and it gets less and less as you go down. Now what else affects the actual strength? So the higher the number of bonds, the stronger the bond. Okay, so triple is stronger than double, which is stronger than single. So let's show you this in a table. So you can see single, double, triple. And the higher the number of bonds, the stronger the bond, as you can see up there. So we can see this bond, as it's called bond energy here, again, enthalpy, energy, interchanged, okay? And you can see that the bond energy is going up and up. Or the bond enthalpy is going up and up and up and up. And as that happens, you can also see that the bond length is going down. So, if we look here, the bond enthalpy increase as the number of bonds increase, and the bond length gets shorter. Okay, so that is how the bond enthalpies are affected by multiple bonds and by the radius of the atoms. Now, last thing before we attempt to question, bond dissociation enthalpies. bond, and I put in brackets dissociation enthalpies because they don't really normally put that word, but sometimes it does appear. And if you can see here, interchange the word enthalpy and energy. I'm only putting that because when you go on the internet, you'll see lots of times they say enthalpy, lots of times they say energy. And you look down here and you can see that the energy put in to break the bond is 436. That's the energy that would be given out if the bond was made as well. Okay? So, and you just get tables like this, and you can use those tables to answer questions. But remember, the most important thing is that it's all endothermic. So basically a bond energy or bond enthalpy is always going to be given in an endothermic way, so in a breaking the bonds type manner. So now we're going to go through the most common type of question that's going to be asked about bond enthalpies or energies. And it's where you're given an equation and then given a small part of a table and then asked to work out what's missing. So here we're working out the NH. And this is the most likely question you're going to get asked because just doing the normal calculations you do in GCSE is deemed a little bit too easy. So let's move that to the side, okay, and then do our calculation. So our calculation is going to be like this. So remember, your delta H is going to be your bonds broken minus bonds made. Okay, so that's your most important thing. And then we go from there. Okay, and we just start putting the bonds in. So your delta H, and I'm going to start with delta H. The delta H of the equation is minus 92. You can see it, so I can put that minus 92 in. Okay, and then the bonds broken is going to be, well, if you look at the equation itself, I've got to break the N2, so it's 1 times N. And I'd always recommend you write it like this. And then I also break 3 times H. Again, I'm just getting it from the equation. 3 there, and there's 3 hydrogen bonds. And that is our bonds broken. Okay. We then minus that away. And we're going to do our bonds made now. So our bonds made is this. So first of all, you need to know what it looks like. So this is ammonia. And there's your hydrogen, how we got that. And then your nitrogen is that. So we got our 1 times NN, which is there, 3 times HH, and then here we've got ammonia. Now we've got 2 ammonias, so there's 1, 2, 3. That means there's 6 times NH. Okay, so we've got 6 times NH, and that's our equation. Now we don't know our NH, but we do know the rest of our stuff, so we know this. So what we can do is we can just substitute the numbers in. So if I substitute the numbers in here, and I just go, right, okay, NN, according to that, is 945. So it's 945 plus 3 times, and the HH is 436. Okay? And then all I do, put that together. And again, I'm still minusing the, let's do it in blue. I'm still minusing the 6 times NH. Okay? If that is the question, and we do some quick calculations, and hopefully you're doing this with a calculator yourself, okay? So if that's made up, that is going to be 2253. Okay, so 2253. Remember, we are still at the point where we have got minus 6 times NH. Now, if you're a maths kind of person, this shouldn't be too bad right now, because remember, this is still minus 92, and all you do is rearrange the whole lot. So I rearrange the whole lot to find this here. So if I rearrange the whole lot, it looks like this. So it basically looks like 2253 minus 92 equals, okay, and that will be equal to my 6 times NH, if we rearrange that. Okay, now I find it easy, because I'm not really a mathematician, is I find it easier to go, right, okay, plus the NH onto that side, and then minus the minus 92 from that side. And that's how I did it, right? Okay, because I'm not really a mathematician, I'm a chemist, not a mathematician. Mathematician, easy, but there are chemists who are not mathematicians. Okay, so if that is the case, let's finish this off. Okay, all we have to do is put this in the calculator. Okay, and the most important thing is when we put it in the calculator, U will end up equaling 2, 3, 4, 5. But the important thing is there's 6 of those, and I want to know it for 1, so I divide by 6. Okay, and then I will get my final number, which is rounded to 3 significant figures, which is 391 kilojoules per mole. Most common question you're going to get, okay, could be any type of equation, could be anything whatsoever, but the most important thing, and the thing everybody always forgets, is divide by however many bonds there are. They often just say, look, the answer is 2, 3, 4, 5. No, there's 6 of them in this case, and for that you've got to know the structures. Okay, so go onto the worksheet that follows this, practice this a lot.